Deep within the vast expanse of the North Atlantic Ocean, a chilling enigma lies hidden. South of Greenland, amidst the turbulent waves, a cold anomaly persists, defying the warming trend gripping our planet. This is the North Atlantic Cold Blob, a region of unusually cold water that has baffled scientists and sparked urgent questions about the future of our climate. The very existence of this cold spot is a stark reminder that our planet's climate is a complex and interconnected system. As the world warms due to human activities, unexpected consequences are unfolding, and the North Atlantic Cold Blob serves as a potent symbol of the profound changes underway. This chilling anomaly is not merely a scientific curiosity, it is a warning sign, a harbinger of potential disruptions to global climate patterns that could have far-reaching consequences for humanity. Imagine for a moment a vast and mysterious pool of cold water quietly nestled amidst an otherwise warming ocean. This isn't just any patch of sea, it's a striking anomaly, a place where the rules of global warming seem to bend, if only for a moment. As the world's oceans heat up, this region remains stubbornly cool, almost as if it's resisting the relentless march of rising temperatures. This phenomenon is known as the North Atlantic Cold Blob. For decades, scientists have observed that while most of the planet's oceans are warming, this particular region has been cooling, its temperatures dropping steadily, year after year. It's a puzzle that has captured the attention of climate researchers worldwide because it stands in stark contrast to the broader trend of global warming. If you look at satellite images or heat maps of the North Atlantic, you'll see it clearly. A deep blue patch south of Greenland standing out like a cold blue thumbprint against a sea of warmer colors. This anomaly is not only visually striking, but it also raises important questions about the health and stability of our planet's climate system. But what is behind this unusual and persistent cooling? What forces are at play beneath the surface, shaping this enigmatic region? The answer lies in a complex interplay of natural forces. Ocean currents swirl and shift, glaciers melt and pour fresh water into the sea, and all of these elements interact within the delicate balance of Earth's climate system. Scientists pore over data, run intricate climate models, and analyze every variable, searching for clues to explain this phenomenon. The North Atlantic Cold Blob is not an isolated oddity. In fact, it is intimately connected to the fate of one of the planet's most important ocean current systems, the Atlantic Meridional Overturning Circulation, or AMOC. This vast, slow-moving system acts as a kind of planetary heartbeat, circulating water and redistributing heat across the globe. Picture the AMOC as a giant conveyor belt, tirelessly transporting warm, salty water from the tropics northward, where it cools and sinks, before flowing back southward as cold, deep water. This process not only helps regulate temperatures across continents, but also influences weather patterns, sea levels, and even the distribution of marine life. When this circulation system is disrupted by melting glaciers, changes in salinity, or shifts in wind patterns, the consequences can be profound and far-reaching. Scientists warn that a weakened or stalled AMOC could trigger dramatic changes in global climate, from more extreme weather events to altered rainfall patterns and even impacts on agriculture and fisheries. The North Atlantic Cold Blob, then, is more than just a curiosity, it's a warning sign, a signal that the intricate machinery of our planet's climate is under stress and that the effects could ripple out across the world. It seems counterintuitive. While the world is experiencing a steady rise in average temperatures due to global warming, there's a mysterious patch in the North Atlantic that's actually getting colder. This phenomenon, often referred to as the North Atlantic Cold Blob, stands out as a striking anomaly in a world otherwise dominated by warming trends. If you look at temperature maps of the planet, you'll notice this blue patch, surrounded by a sea of red and orange, raising questions for scientists and the public alike. This paradox highlights just how intricate and interconnected Earth's climate system truly is. Every component, from the swirling ocean currents to the shifting winds in the atmosphere, plays a role in shaping our planet's climate. When one part of the system changes, it can set off a chain reaction, sometimes with unexpected results. The North Atlantic Cold Blob is a perfect example of how local and regional climate effects can differ dramatically from the global average, reminding us that climate change is not a simple, uniform process. The main driver of global warming is the buildup of greenhouse gases like carbon dioxide and methane, which trap heat in the atmosphere and cause average global temperatures to rise. But these same emissions also set off a cascade of secondary effects. For instance, as the planet warms, polar ice melts at an accelerated pace, and this melting can have surprising regional impacts, sometimes even leading to cooling in certain areas, despite the overall warming trend. One of the most significant contributors to the North Atlantic cold blob is the massive influx of fresh water from melting glaciers in Greenland and the Arctic. As these glaciers retreat, they release enormous volumes of cold, fresh water into the salty North Atlantic. This process is happening faster than ever before, with some estimates suggesting that Greenland alone is losing hundreds of billions of tons of ice each year. The scale of this melt is staggering. Rivers of glacial meltwater pour into the ocean, carrying with them not just water, but also sediments and nutrients. Icebergs, once locked in place for centuries, now drift freely into the North Atlantic, further freshening the surface waters. This sudden and massive addition of fresh water is fundamentally altering the ocean's chemistry and physical properties. The influx of fresh water disrupts the delicate balance of salinity and temperature that drives one of the world's most important ocean currents, the Atlantic Meridional Overturning Circulation, or AMOC. The AMOC acts like a giant conveyor belt, moving warm, salty water northward and bringing cold water back south. When too much fresh water enters the system, it dilutes the salty water, making it less dense and less able to sink. This weakens the AMOC's flow, slowing down the entire circulation pattern. As the AMOC slows, less warm water is transported from the tropics to the North Atlantic. This reduction in heat delivery leads to a localized cooling effect, especially in the region known as the cold blob. The result is a striking paradox, a patch of ocean growing colder in the midst of a rapidly warming world. Scientists are closely monitoring this region, as changes in the AMOC could have far-reaching impacts on weather patterns, sea levels, and even the stability of the climate system itself. Imagine for a moment a giant conveyor belt tirelessly circulating warm and cold water throughout the Atlantic Ocean. This conveyor belt isn't made of metal or rubber, but of water, vast, powerful, and essential to life on Earth. It's invisible to the naked eye, yet it shapes the climate of entire continents, influences the weather we experience every day, and even affects the delicate balance of marine ecosystems. Without this constant movement, the world as we know it would be a very different place. This is the AMOC, or the Atlantic Meridional Overturning Circulation, and it's a crucial component of Earth's climate system. Scientists have spent decades studying its patterns, using advanced technology and research vessels to map its flow and understand its impact. The AMOC acts as a global thermostat, redistributing heat and helping to keep temperatures in check across the planet. Warm surface water flows northward from the tropics, carrying heat to higher latitudes. This journey is vital, as it brings warmth to regions like Western Europe, making their climates much milder than other places at similar latitudes. The energy transported by these currents is immense, and it's a key reason why cities like London or Paris don't experience the harsh winters found in other parts of the world. As it cools near the Arctic, it becomes denser and sinks, flowing southward in the deep ocean. This sinking motion is like the engine of the conveyor belt, pulling more warm water northward and keeping the cycle going. The process is driven by differences in temperature and salinity, creating a powerful force that moves water thousands of miles across the globe. This continuous circulation, helps regulate global temperatures and weather patterns. It's responsible for distributing heat, influencing rainfall, and even shaping the paths of storms. The AMOC's reach extends far beyond the Atlantic, affecting weather systems in North America, Europe, and even Africa. When the conveyor belt is running smoothly, it helps maintain the balance that supports life on Earth. However, this delicate balance is being disrupted by the influx of fresh water from melting glaciers. As global temperatures rise, glaciers and ice sheets are melting at unprecedented rates, pouring vast amounts of fresh water into the ocean. This isn't just a distant problem, it's happening right now, and the consequences are already being felt. Greenland, which is home to the world's second-largest ice sheet, is losing ice at an alarming rate. Every year, billions of tons of ice melt away, much of it flowing directly into the North Atlantic. This rapid melting is one of the most visible signs of climate change, and it's having a profound impact on ocean circulation. As the ice melts, it pours fresh water into the North Atlantic, a bit like adding a pitcher of cold water to a warm bath. This sudden influx of fresh water dilutes the salty ocean water, making it less dense and less likely to sink. The more fresh water that enters the system, the weaker the engine of the conveyor belt becomes. This disrupts the sinking of dense, salty water that drives the amok. When the water doesn't sink as it should, the entire circulation slows down. This slowdown can have ripple effects across the globe, altering weather patterns, changing ocean habitats, and even threatening food security for millions of people. The conveyor belt slows down, reducing the northward flow of warm water and contributing to the cooling effect observed in the North Atlantic cold blob. This region, marked by unusually cold ocean temperatures, is a warning sign that the system is under stress. If the AMOC continues to weaken, the impacts could be dramatic, shifting weather patterns, more extreme storms, and unpredictable changes to the world's climate. The melting giants of the North are sending a clear message: the balance of our planet's climate is more fragile than we once believed. The AMOC, weakened by the influx of fresh water, sets off a domino effect across the global climate system. Like a stone thrown into a pond, the impacts ripple outward, disrupting weather patterns, altering ocean currents, and influencing temperatures far beyond the North Atlantic. One of the most significant consequences of a weakened AMOC is the potential for colder winters in Europe. The warm water carried northward by the AMOC helps moderate temperatures in Western Europe, making winters milder than they would otherwise be. As the AMOC slows down, this moderating influence diminishes, leading to colder and harsher winters. Additionally, a weakened AMOC can disrupt rainfall patterns, potentially leading to increased drought in some regions and increased flooding in others. The interconnectedness of Earth's climate system means that changes in one part of the system can have cascading effects across the globe.